A scientific mystery. Have you ever seen something move all by itself? I mean really move, with no one pushing it and no engine humming away. It sounds like something out of a magic show, right? But sometimes, the most amazing magic is just science we haven't explained yet. Imagine a small disk of ice sitting quietly on a surface. Then, without warning, it starts to glide. It picks up speed. It zips across the surface as if it has a mind of its own. This isn't a trick. This is a real phenomenon that scientists are exploring right now. So, let's put on our thinking caps and our safety goggles, because we are about to dive into the fascinating science of how and why things move in unexpected ways. Let's start our scientific journey in a familiar place, the kitchen. Have you ever sprinkled a few drops of water into a very hot frying pan? If the pan is just warm, the water sizzles and evaporates quickly. But if the pan is really hot, much hotter than boiling temperature, something incredible happens. The water droplets don't just boil away instantly. The bottom of the droplet immediately vaporizes, creating a thin, insulating cushion of gas that lifts the droplet up. This vapor layer acts like a tiny hovercraft. The droplet floats and can glide with almost no friction. This is called the Leidenfrost Effect, first described in 1751 by Johann Gottlob Leidenfrost. The steam cushion is a poor conductor of heat, so it protects the droplet and slows evaporation. Leidenfrost gives us two key ingredients, levitation and reduced friction, that let droplets glide with ease. Now let's travel from the kitchen to a cutting-edge laboratory at Virginia Tech. A team led by Jonathan Barreto asked a simple but profound question. Could a block of ice do something similar on a room temperature surface? Instead of heat turning liquid into gas, the warmer surface melts the ice, creating a thin liquid layer underneath, an upside-down version of Leidenfrost. The heat from the plate melts the bottom of the disc, producing a super-thin meltwater film trapped between ice and aluminum. That liquid layer lifts the ice slightly, creating a nearly frictionless surface. The ice hydroplanes on its own meltwater. But a slippery layer alone isn't enough to make the disc move on its own if the surface is flat and symmetric. What matters is how the meltwater escapes. As water flows out from under the disc, it creates a reaction force, like a rocket exhaust, that can push the disc. If the flow is asymmetric, forces don't cancel. The disc will be propelled opposite to the exiting water. By designing the surface to guide meltwater one way, they effectively built a microscopic water jet engine powered by melting. To control the flow, they milled microscopic channels into the aluminum plate, a herringbone pattern. Herringbone looks like connected V-shapes, all pointing the same way, perfect for guiding fluid. As the disc melts, water is drawn into these tiny channels by capillary action, the same force that pulls water into a paper towel. The V-shape funnels and focuses the water so it exits as a unified stream on one side of the disc. Newton's third law, every action has an equal and opposite reaction, explains why the jet propels the disc forward. If the channels force water to exit backward, the disc moves forward, a self-propelled vehicle powered only by melting. By heating the plate more, they increase melt rate, strengthening the flow and speeding the disc. They effectively created a micro-water jet engine. Thermal energy turned into mechanical motion through clever surface design. The team then sprayed a hydrophobic coating over the patterned plate. And the results were surprising. Hydrophobic surfaces repel water, so meltwater began to bead up instead of flowing smoothly. Under the disc, a flattened droplet formed and was pinned to the rim, stretching and storing energy as more melt accumulated. The coating also adds nanoscale roughness that initially locks the disc on the ridges between channels. When the stored surface tension energy becomes too great, the droplet snaps free and contracts rapidly. That contraction fires a backward jet of water and slingshots the ice forward with a dramatic burst of speed. This stick-slip motion stores energy while stuck and releases it explosively, like a tiny cannon. The team had discovered an even more powerful mode of propulsion driven by surface tension. Surface tension, the same force that lets insects walk on water, became the engine of this slingshot effect. This lab discovery connects to a decades-old natural mystery, the sailing stones of Racetrack Playa in Death Valley. Huge rocks seem to move on their own, leaving long meandering trails in the dried mud. Scientists found the answer. Rare conditions create a thin layer of water, which freezes into large sheets of window pane ice overnight. As the sun warms the playa, the ice breaks into panels that drift in light winds and nudge rocks across the mud. In the field, the driving force is wind on ice flows. In the lab, it's meltwater jets. But both rely on thin liquid layers to reduce friction. The sailing stones are a giant, natural, much slower version of the same physics we see in Virginia Tech's experiments. Both stories show how ice plus water equals low friction and surprising motion. Science often reveals that nature and lab-scale experiments are 2 pages of the same book. Discovering a new principle is exciting, but the power of science lies in application. One application is de-icing. Smart surfaces could help shed ice on airplane wings, power lines, or wind turbines. Another is tiny self-powered devices, micro-robots or sensors that move using small thermal differentials or phase changes. A sublimating pellet, solid to gas, could create a vapor cushion and propulsion without batteries. Surfaces could be engineered as conveyor belts with no moving parts, passing objects via sequential slingshot zones. This is thermal to mechanical conversion. Waste heat could power microtasks or harvest energy at small scales. It could move fragile components contactlessly or sort tiny particles with precision. From self-cleaning glass to medical micro-devices, the possibilities are wide. From a dancing water droplet on a hot pan to an ice disk shooting across a lab bench, we've seen surprising physics at work. A simple observation, curiosity, and clever engineering opened a new path for motion and energy. Herringbone highways and surface tension slingshots are blueprints for future smart surfaces and devices. Not just curiosities. They point toward safer travel, more resilient infrastructure, and new low-energy technologies. This is the heart of scientific exploration. Ask questions, experiment, and look at old problems in new ways. Next time you see water sizzle in a pan or ice melt on a sunny day, remember, extraordinary science can be hiding in plain sight. Keep asking, keep experimenting. The science of today builds the world of tomorrow. Thank you for watching.